So design of an RC section for shear as per IS 456 2000. In an RC beam section, the combined effect of bending and shear is taken by, that is, you are having, suppose you are having a beam like this, a simply supported beam. Then if I am drawing the bending moment, it will be coming like this. So this is W kilonewton per meter is the factored load. W kilonewton per meter is a factored load. And then this value is W L square by 8, and the shear force will be coming like this. The shear force will be WL by 2 and WL by 2. So the effect of this shear force and the bending moment in an RC beam is taken care by first one, that is the concrete, the second one the main reinforcement, and in order to take the shear we will be providing what, the shear reinforcement, that is the combined effect of bending and shear will be taken by these three, that is the concrete which is present, the main reinforcement which we are providing for flexure, and the shear reinforcement with addition which we are providing to take the effect of shear. That is the combined effect of these two will be taken by these three elements in your section, a reinforced section. Okay, that is the design process for the check for shear. The first one is you need to identify the critical section where the shear is maximum. That calculate the shear force at the critical section of the beam. As you have seen here, the maximum force, shear force is coming at this support, which means the critical section will be at this support. That is WL by 2 is the maximum shear force, and when it is moving away from the support, this shear force is decreasing. As a result, the maximum shear force will be coming at this support. But the code suggests certain other or certain changes in the critical section of your shear force. That is, it gives in clause number 22.6.2.1 of your IS 456 2000. You can see the critical section for shear. The shear computed at the face of the support shall be used in the design of the members at this section, except as given in 22.6.2.1. That is, whatever be except in this section given, the shear is to be computed at the face of the support. That is, we need to compute the shear at the face of the support. That is what we had done. That is your WL by 2. But when clause number 22.6.2.1, when the reaction in the direction of the shear, applied shear introduces compression into the end region of the member, the section located at a distance d from the face of the support may be designed for the same shear as that computed at the distance d. That is, you can read it once more. When the reaction in the direction of the applied shear introduces compression, that is, if I am having a simply supported beam like this, if I am having a simply supported beam and taking half part of it, you're having your wall or your support like this. The induced, there will be compression induced like this at this support, right? There will be, due to reaction, there will be compression there. The reaction will be in this form, and there will be compression induced at the support. That is, when the reaction in the direction of the applied shear introduces compression in the end region of the member, the section located at a distance less than d from the face of the support may be designed for the same shear. That is, if I am having the shear force diagram like this, the shear force diagram like this, and taking only half part of it, like this is WL by 2. Then at a distance d from here, suppose this distance is d from the face d, then the variation of shear stress is not considered. That is, there is no variation of shear stress. We will consider at a distance d from the face of the support. The face of the support may be designed for the same shear as that computed at distance d. That is, we will consider this as the critical section. Critical section, that is, for uniformly distributed load. The above clauses are applicable for beams generally carrying uniformly distributed load, or when the principal load is located farther than 2d from the face of the support. So a simply supported beam having UDL, I could take the critical section for your shear force at a distance of d from the face of the support. Okay, that is, I will calculate the shear force, critical section for shear force at a distance of d from the face of the support. That is, after the or up to d only I will calculate. There is a variation for shear force, and after this, or in this portion, there is no variation. The shear force is uniform. I will not consider the shear force as varying, and this value of shear force, that is, this value of shear force, this value for shear force will be your design shear force value, shear force value. This value of shear force will be design shear force value. Now, can you tell if I'm designing for this WL by 2, will it be safe? Definitely it will be safe because the design shear force according to your IS 456 only up to here. So if I'm designing for WL by 2, this is a higher shear force value, which means it will be safe. So in the numericals, actually we will be designing for WL by 2. Okay, actually you need to design for a more economical section. Your design shear force is this one. So in some of the textbook, you can see the design shear force is taken this value. But if you're going for that, you will take more time. That's why we will go for your maximum shear stress value, the shear stress value, force value, that is WL by 2 at this support, such that we can directly start with the numericals. You can see in the figure number 2 the typical support conditions for locating factored shear force. For a simply supported beam, we can see from the face of the support to distance D. Here also this is a beam column connection. You can see here also it is the at a distance of, this is a column, this is actually a beam, and this is another column. So this is a beam column connection. There also the critical section for shear, it is at a distance of D from the face of the support. And here this is a cantilever beam. Cantilever beam, you can see for a cantilever beam, the section is not reducing compression at the support. As a result, this face of the support is taken as the critical section for your shear force. That is, you can see here, this is the critical section for, this is the critical section for shear force. This section is taken as the critical section, and here you can see this is a critical section, and for a beam column connection, you can see this is a critical section. Okay, the same thing you can see here also, it is explained in this critical section for shear for a cantilever. You can see at the face of the support, this is at a distance D from the face of the support. And if there is a heavy load, heavy load of heavy load between 2D, then the section you need to take the critical section at the face of the support. If there is a heavy load of 2D, if heavy load within 2D of your support, then you need to take the critical section at the face of the support. Otherwise, you can take it at a distance of D from the face of the support. I hope this is clear for you. Now, the design process, that is the first what I discussed, to calculate the shear force at critical section of the beam, that is VU. We will denote this by VU. Okay, that is a critical section shear force. We will denote by VU. Clause number 22.6.2.1. You can see as a summary, we will say that if the support reaction is creating compression in the end region of the member, then the section located at a distance less than D from the face of the support may be designed for the same shear as that computed at distance D. That is, in your this question can be asked for your gauge and all. What is the critical section for shear for a simply supported beam, for a cantilever beam? If there is a heavy load present at less than 2D from your face of the support, such questions can be asked. Okay, so I hope you are clear with that. Now the next one is calculate the nominal shear stress. Given in clause number 40.1, you can see nominal shear stress here means it is denoted by tau v. It is the actual shear stress. Now you have got the value for your shear force. Now you need to calculate the shear stress value. That is the nominal shear stress value. That is denoted as tau v. That is the actual shear stress. That is, you will get the actual shear stress or the nominal shear stress is equal to VU. That is the actual shear force, which is due to the applied load and the dead load. Applied load and the dead load divided by BD. Here we will take effective depth. Please take care of that. We will take the effective depth only. That is, you can see in clause number 40.1, the nominal shear stress. The nominal shear stress is beams of uniform depth shall be obtained by the following equation. Tau v is equal to VU by B. It's not suffix, it is B into D, where VU is the shear force due to design load. VU is the shear force due to design load. B is the breadth of the member, which for flange section shall be taken as the breadth of the web. That is, if it is a normal rectangular section, there is a normal rectangular section, you can take B, and this is your effective depth, you can take it as D up to center line of your reinforcement. Now, if it is a T beam, if it is a T beam or a flange beam, you can take this as BW as your B. This is BW, that is a change. So tau v, the actual shear stress or the nominal shear stress, is equal to VU by BD, where VU is the shear stress at the shear force at the critical section, and B is the width of the beam, and D is the effective depth of the section. So the above shear stress must be less than a value that is your tau C max. That is, whatever shear stress value I got here, this tau V must be less than some value known as tau C max. With shear reinforcement, that is, under no circumstances, even with shear reinforcement, shall the nominal shear stress in beams tau V, that is the nominal shear stress or the actual shear stress tau V, exceed tau C max given in table number 20. That is, in under no condition or in no case, the tau V should be greater than tau C max. Now you will understand what is tau C max. It is given in table number 20, the maximum shear stress. It depends on the grade of the concrete. That is, for the different grade of concrete, the code suggests the tau C max value, that is, for M15 it is 2.5 Newton per mm square. For M20 it is 2.8. For M25 it is 3.1. It goes like that. Okay, that is, the code suggests the tau C max value for the different grade of the steel. And this tau C max is the maximum allowable values of shear stress in concrete with shear reinforcement. That is, if I am telling, and in no case it should be greater than tau C max. So tau V should be greater than tau C max. That is, the yielding of the shear reinforcement at the ultimate limit state is essential to ensure a ductile failure. You have studied this in case of your over reinforced section and under reinforced section. What happens in an over reinforced section? In an over reinforced section, there occurs a brittle failure, right? There occurs a brittle failure. It is because the reinforcement will is given in a higher amount. As a result, in simple way, if I'm saying the reinforcement is given in a higher amount, as a result it won't yield at the time of failure. In fact, the concrete will yield at the time of failure, and as a result what will happen, a brittle failure will take place. Similarly, if I'm providing a large amount of shear reinforcement, what will happen? The shear reinforcement at the ultimate limit state won't be yielding. That is, it won't fail because the amount of reinforcement provided is very much high. As a result, there won't be a ductile failure, and as a result, there won't be ample warning for to escape. So, however, such a failure will not occur if the shear reinforcement provided is excessive. What will happen? If the shear reinforcement is provided is excessive, there won't be yielding of your reinforcement. If the total cross-sectional area ASV, we'll tell you this, what is this ASV? This is actually A suffix SV, okay, ASV of the stirrup legs, and the if the total cross-sectional area ASV of the stirrup legs and the bender bars exceeds a certain limit, it is likely that the section becomes stronger in diagonal tension compared to diagonal compression. So what happens is that it will not fail in diagonal tension, it will fail in diagonal compression, and as a result, there will be a brittle failure. Such a situation is undesirable due to the brittle nature of the failure. Moreover, it turns out to be uneconomical in much the same way as over reinforced beams. In order to prevent such shear compression failures and to ensure yielding of the shear reinforcement at the ultimate limit state, the code has indirectly imposed a limit on resistance of Vu by limiting the ultimate shear resistance. That is, if tau V is greater than tau C max, there is no other option but to change the beam size so that tau V is less than tau C max. In no case we should increase this value for tau C max. Have you understood this? Why we have gone to tau C? We have limited to tau C max because there should not occur a there should not occur a brittle failure. So the design shear strength of the concrete. Now there is a new term, that is tau C. That is a design shear strength of the concrete. At the beginning of the lecture, I told you. Do you remember? At the beginning of the lecture, I told you. In an RC beam section, the combined effect of bending and shear is taken care by concrete, main reinforcement, and shear reinforcement. So based on this concept, I am going to tell you certain things. Okay, that is based on this. That is, the combined effect of the shear and bending is taken by concrete, main reinforcement, and shear reinforcement. And I recommend and I tell you to keep this thing in mind. You must always keep these three things in mind. That is, the effect of shear and bending, combined effect of shear and bending is, so it is taken by concrete, main reinforcement, and shear reinforcement. If you keep these three in your mind, easy to understand the design procedure for a shear design. Yeah, that is the design strength of the concrete. The value of shear stress resisted by the concrete and main reinforcement. That is, there are actually three members taking the shear. Here, the main concrete, the shear value of shear stress resisted by the concrete and main reinforcement is called as the shear strength of the concrete. That is, out of the three, the concrete and main reinforcement will be taking some shear stress, and that value is called as tau c. Okay, that is, you can see in table number 19 of your IS 456 2000. So keep in mind, tau V is the total shear stress that is coming due to the applied load. Out of that, tau C is taken by the concrete and main reinforcement. So keep in mind like that, okay? Now, table number 19 of your IS 456 2000 gives the value for tau C, that is table number 19, design shear strength of concrete tau c in Newton per mm square. So you can see here, this is 100 AS by BD. I'll call it as 100 AS by BD. That is your, I'll denote it as PT percentage. That is your percentage of tension reinforcement. This 100 AS, where AS, the term AS is the area of longitudinal tension reinforcement. See, it is the AS is the area of longitudinal tension reinforcement which continues at least one effective depth beyond the section being considered except the support where the full area of tension reinforcement may be used provided the detailing conforms. So you just need to understand the AS is your AST, that is your area of steel under tension. I repeat, area of steel under tension. It is 100 AS by BD will give you the percentage of tension reinforcement. So from table number 19, you have 100 AS by BD value. If you take 100 AS by BD value, suppose I got this value as in 1.12. I got this value as 1.12. So this value lies between 1 and 1.25, right? This value lies between 1 and 1.25. That is, I can say it lies somewhere here. It lies somewhere here, isn't it? It lies between 1 and 1.25. Now consider I'm taking M20 grade concrete. M20 grade concrete. So this design strength of the concrete, that is tau c, depends on percentage of tension reinforcement PT as well as the grade of concrete. So I can say it lies between, suppose I'm taking it as an example 1.12, then it lies here and between here, that is 1 and 1.2. You can get the value corresponding to M20. It lies between 0.62 and 0.67, isn't it? For M20 it is 0.62, and for 1.25% of steel it is 0.67. So for 1.12 it lies between 0.62 and 0.67, and we will find this value by linear interpolation. I'll tell you how to find this value by linear interpolation when we are discussing on the numerical. So you time being, you understand, for finding the design strength of the value, you need to get the value for your percentage of tension reinforcement, and it depends on the grade of concrete. And you need to understand how you're taking it. That is, for one, you have the value, as 0.62 for M20, and for 1.25, you have the value as 0.67. Interpolating, that is linear interpolation, you'll get the value for your 1.12. Okay, and that we'll discuss when we are discussing the numericals. The value of tau c depends on, first of all, the value of tau c depends on the grade of concrete. That is what we have discussed here. It depends on the grade of concrete. That now the next one is it depends on the percentage of tension reinforcement, that is 100 AS by BD. So the question can come like this. That is, the value of tau c depends on the grade of concrete, width of the section, effective depth of the section, area of tension reinforcement. Like that, the question can come. Understood? So the next one is you got the value for tau c, that is the shear stress taken by concrete and main reinforcement. So the shear force resisted by the concrete and main reinforcement, I'll be denoted by VUC, V suffix UC. That is the shear force taken by the concrete and main reinforcement. Now you know the value for the shear stress taken by the concrete and main reinforcement multiplied by the cross section will give you VUC. That is the shear force resisted by the. Yes. Now tell me, when tau V is greater than tau C, what does that mean? So this is the prime thing you need to understand. When tau V is greater than tau C, there is some force, or there is some strength to be provided by your shear reinforcement, right? Definitely, because the whole main reinforcement and the concrete cannot alone take the shear that is coming, and definitely we should provide some shear reinforcement, isn't it? Now, if tau v is less than or equal to tau c, theoretically, there is no need of providing shear reinforcement because the shear will be taken by your concrete and main reinforcement, but we need to provide a minimum shear reinforcement. We need to provide a minimum reinforcement. I'll tell you what is the reason for that. We need to provide a minimum reinforcement. And in case that is when tau is very much less, that is where tau is less than or equal to tau c by 2, then there is no need of providing shear reinforcement. And these structures will be of structures of lesser importance. Okay, that is there this shear stress will be very much small, or the shear stress will be very much less than tau c by 2, then there is no need of providing shear reinforcement. Is it okay? Is it okay? Now, when tau is less than, there will in order to have enough ductility, we provide the minimum reinforcement. If we don't provide that, there won't be a ductility in the structure, and as a result, we provide the minimum shear reinforcement given in when tau is less than tau c. Now we understood up to here, that is VUC, that is the shear force resisted by the concrete and main reinforcement. Now the shear force to be resisted by the shear reinforcement, I can take it as design shear reinforcement. I'll be denoting it by VUS. VUS. VUS, I can write it as VUS is equal to VU minus VUC, right? Have you understood that? That is the shear reinforcement can be provided when VUS is equal to VU minus VUC. This much amount of shear has to be resisted by the shear reinforcement. So I hope you are clear with this. I hope you are clear with this. And value for this VUS, you can start from here. The shear reinforcement shall be provided to carry a, I'll discuss what is written here. The shear reinforcement shall be provided to carry a shear force equal to VU minus tau c into BD. That is, tau c into BD is here VUC, the shear force resisted by the concrete and main reinforcement. The strength of the shear reinforcement VUS shall be calculated as below. For vertical stirrups, VUS is equal to 0.87 FY ASV D by SV. For inclined stirrup, it is 0.87 FY A. It is 0.87. Okay, it's not 0.8.7. It's 0.87. 0.87 FY ASV D divided by sine SV into sine alpha plus cos alpha, where alpha is the angle of inclination of your bars. And for bender bar, if you are using, then the corresponding equation is this one. And you know this values, this terms represented. The only new term for you is ASV, where ASV is the total area of the cross section depending on the type of stirrup being provided, and SV is the spacing of the stirrups or bender bars along with the length of the member. That is, if I'm providing the shear reinforcement, there will be some spacing, and SV represents the spacing of the shear reinforcement. Okay. Now, some important points that to be taken care while designing for shear. The first one, the bender bars cannot be provided alone. That is, it is always provided along with the vertical or inclined shear reinforcement. That is, when you are if you are planning to provide bender bars, you should not provide it alone. It should be provided along with your vertical bars, vertical stirrups, or your inclined shear reinforcement. The main reinforcement bend at suitable angle are called as bender bars. The bars should not be bent up at the center half portion. That is, if you are having your bars like this, if you are having your beam, this is the cross section, longitudinal section of a beam. You are having your bar like this, one tension reinforcement going in this way, then there is another tension reinforcement going the same way. Then the bender bar should not be bent at this position. At the center half, you should not bend, because this reinforcement is provided to carry the enough bending moment coming at this section. So it should always be bent up at the supports. And this distance, the first distance is as root 2a. I will tell you what is this root 2a when we are discussing the numerical. So this is provided in our SP34, SP34, that is special publication 34 for your IS 456. SP34 4. IS 456 2000, that is special publication 34 for IS 45 2000 is 2000, that is here detailing of the structure is given. There is the detailing and drawings and detailing of the RC elements are given. There you are provided with what is the distance for your first bender, then the corresponding what is the next. If you are bending two bars, then what is the distance for your next bender? Such kind of things are detailed in your IS 456 XP13 SP34 for your IS 456 2000. I have given this in your Google Classroom. You can download it from there. You can read it. Most of the things which I said while drawing or explaining the beam, you can see it over there. Now, the minimum shear reinforcement. The code suggests in clause number 26.5.1.6, you can see the minimum reinforcement, that is ASV by the small b. Okay, BSV must not be greater than zero point 0.4 by 0.87 Fy. You can see in clause number 26.5.1.6, that is ASV, that is the area of shear reinforcement based on your number of stirrups, divided by BSV must not be greater than zero point 0.4 by 0.87 Fy. So I can write this, rearranging this, I can write the maximum spacing or SV must be less than or equal to 0.87 Fy ASV divided by zero point 0.4 into small b. Okay, that is the width of the beam. 0.4 into b. That is, the code gives in clause number 26.5.1.6 the minimum shear reinforcement. So based on this, I can say the maximum spacing based on this minimum shear reinforcement is what? SV must be less than or equal to 0.87 Fy ASV by zero point 0.4 b. That is to avoid development of, I told you why we are providing minimum reinforcement. At this time, I told you when we are discussing on this tau v less than or equal to tau c, I told you there is no need of shear reinforcement, but provide minimum reinforcement. And the reason for that is to avoid development of cracks due to any reason such as due to creep and shrinkage. Due to the creep load and shrinkage load that can be cracked, to avoid that, we provide the minimum reinforcement. Due to sudden increase of load or stresses due to temperature variation or increased ductility of the member, we provide this minimum reinforcement. Even though the reinforcement is not required, shear reinforcement is not required, we'll go for providing the minimum reinforcement. Now, the maximum spacing is given in clause number 26.5.1.5. The maximum spacing based on your minimum shear is given as 0.87 Fy ASV by zero point 0.4 B. And the code suggests another two methods also to find the maximum spacing. That is, if it is vertical shear reinforcement, the maximum spacing that can be given is 0.75 D. And if it is an inclined shear reinforcement, the maximum spacing that can be given is D. And the spacing in no case should be greater than 300 mm. That is, the spacing in no case should be greater than 300 mm. Okay, I'll just conclude the session. Yes, the design step for shear. The first one is the calculation of VU. This is a summary of this class, calculation of VU. After calculating VU, you need to calculate the value for tau V. That is, this VU is the actual shear force coming, that is WL by 2. That is WL by 2. Now, the second one is calculation of tau v, that is your nominal shear stress, that is tau v, you'll get it as tau v is equal to VU by BD, isn't it? Isn't it? Now from table number 19, sorry, from table number 20, calculate the value for tau c max. This tau v must be less than tau c max for all cases. It should not be greater than tau c max. And if it is greater than tau c max, you can change the section dimension. The fourth step is, now we have calculated up to tau c. Now the fourth step is to calculate the value for your tau c from table number 19. That is, you need to calculate the value for tau c from table number 19. That is the shear taken by the main reinforcement and concrete. That is, from table 19, you'll get the value for tau c. That is shear stress taken by concrete plus main reinforcement. Isn't it? Isn't it? Now the fifth one, if tau v greater than tau c, then we need to go. We need to provide shear reinforcement. Okay. Now the shear reinforcement you can provide in any of the form, that is either vertical stirrups or inclined stirrups or bender bars with vertical or inclined stirrups. That is, we should always provide vertical bars with inclined or stirrups. Nowadays, we don't go for providing inclined stirrups as well as bender bars. Instead, we will go for providing vertical stirrups. And there is another thing that you will study while we are discussing bond. That is, we'll go for curtailment of the reinforcement, and will not provide this bender bars. We'll only provide what vertical stirrups. That is, most of the cases nowadays we won't provide this inclined stirrup as well as bender bars. We will only provide vertical stirrups, but we will study how to design the shear reinforcement when we are providing vertical stirrups and bender bars in the coming lectures. After, if toe V is greater than toe C, you need to provide shear reinforcement, and if toe V is less than toe C, then you need to go for providing minimum shear reinforcement. So I can write, now we got the value for toe V and toe C. Now we will get the value for VUC as toe C into BD, isn't it? Now sixth one, that is the shear force taken by your, this is your shear force taken by your concrete and main reinforcement. So VUS, I will get it as VU minus VUC, isn't it? That is the shear force to be resisted by your shear reinforcement. So if I'm providing vertical stirrup, if vertical stirrups are provided, then I can write VUS is equal to 0.87 FY ASV D divided by SV, isn't it? This is the equation, right? That is VUS is equal to 0.87 FY ASV divided by SV. This value is known to you now. That is the shear force to be taken by your concrete. Fy is known, ASV is known, D is known. From here, you will get the value for the spacing required for the shear reinforcement. So that is the design thing that you are providing. From here, if you get the spacing, you need to calculate the maximum spacing that can be provided based on the three criteria. That is your, now you'll obtain the value for SV value will be obtained. SV value will be obtained. This must be checked for maximum spacing criteria. Maximum criteria. So this is the design procedure for design of a shear reinforcement. So that's all for today's lecture. Hope you have understood this. We will come with the next lecture on numericals for design of shear reinforcement. Thank you and have a nice day.